Here's another problem that we'll analyze using Newton's laws. In this case here, there's a mass M2 sitting on a tabletop and a hanging mass M1. Light massless rope, massless pulley. The question once again will be something like, what is the tension in this rope? What is the acceleration of the system? That's what we'd like to find. The procedure we're going to follow is going to be the same as all the ones that we're following here. We're going to recognize that Newton's laws in a convenient form definitely are going to be our guide here. One for a sub x, one for a sub y. We're going to identify the forces on both masses. We're going to identify a sign convention, and we're going to use 3 and 4 to fill in equations 1 and 2, and that will pop our answers. So let's just begin then with step 3. Let's identify forces. If I look at M1 right here, there's definitely a weight down, and there's going to be an upwards tension. On M2 over here, there's going to be a rightwards tension, and I know that because tensions always pull away from their points of contact, and if we have a T on one side, we'll have a T on the other, because it's a light massless rope. Tension is the same throughout. I'm not going to label this T1 and T2 because it's going to be the same tension. And also on M2, M2 has a weight down because the problem is taking place near the Earth, M2, and it also has a normal force pushing straight up. And that's because the object sits on a surface here and is causing some molecular flexion of the surface, so it will have a normal force up. So I properly identified all the forces on both blocks. I'm done with step 3. Step 4 says identify the signs. We like to call down negative. I'll go ahead and do that and call that a minus m1g the weight. But if down is negative here, the opposite direction out must be positive. That's going to be a positive t. Now, tensions on opposite ends of ropes have opposite signs, so this is a plus t. That's going to be a minus t. So that sets the sign convention along the direction of motion, and I think I'm set there. I don't have to worry about that anymore. I'll do the same for the other direction now. We like to call down negative, so I'll go ahead and call weight negative. That way I'll call the normal force positive, and I have all the signs. So I've successfully completed steps 1 and 2. Recognizing Newton's laws will be my guide. I've just completed steps 3 and 4, identified the forces and the signs. Now I'm going to use this information to fill in equations 1 and 2 and see what I get. So, for mass M1, I'm not going to use equation 1 because mass 1 here doesn't have any forces left or right. So the equation is there, available, and I could use it, but it's just not necessary since there's no x forces. So I'll go right with the next one here. That says AY is the sum of the y forces divided by m. And if I fill all this stuff in here, I'll get something like AY. Let's see the sum of the y forces. I have a plus t, I have a minus m1g down, and I divide all that by m1. And you can put a box around this equation here. So you've just found an equation that links the acceleration of this block in the y direction with the tension and all the other variables m1 and g in there. Okay, now I'll move over to mass m2. If I look at M2, I do have both x and y forces on this block, so I'll use equations 1 and 2 in this particular problem here. So I can just start out and say the x acceleration is the sum of the x forces divided by m. And if I fill all that stuff in, ax, the sum of the x forces, what do I have? If I look at this block here, I just have a single t in the x direction, that's it. So minus t, there's no other x forces, so that's it. It's just a single term sum divided by m2. That's all we'll have there. Minus t divided by m2. Put a box around that, you just found the x acceleration of that mass on the table. There are y forces on M2, that block sitting on the table, so I can use the sum of the y forces divided by m. And if I fill in this particular sum, I'll get hy, the sum of the y forces. I see 2 y forces on this block. I see a normal force up and I see a weight down. So I'll go fill this in. I see a plus n minus m2g divided by m2. Here's my y acceleration. And you can put a box around this, and you're essentially done. You finished step 5. You filled in equation 1 and 2, but there's a bit of interpretation now to figure out, well, what do you have? What did Newton's laws deliver to you? Well, if you look carefully at the problem then, the y acceleration of m1 up or down is definitely linked to the x acceleration of m2 because that's with a rope and pulley tied together. If m1 moves down, m2 must move towards the right. If m1 moves up, M2 must move towards left. That's what the linkage of this rope in here is. So what that tells me then, it tells me that the x acceleration of M2 must be equal to the y acceleration of M1. So these two accelerations are equal to each other because they're tied together by a rope. We have another video that you can watch that discusses that objects tied together by a rope have the same acceleration. So those two things would be the same. So a couple of things you can do then is you could just replace this symbol with a and a if you want, or because they're the same, you can just equate the two equations and you can immediately begin solving and get an answer to come out. So I'll go ahead and just equate the two equations over here on the left. So I'll just say that plus t minus m1g over m1 is equal to minus t over m2. And I can put a box around this. So what you can do now with just basic algebra here is you can solve this for T, and that will give you the tension in the rope. There's your first answer right there. Now, if you wanted to, when you're done with that, when you have this tension, what you can do with this T now is take this T and plug it into T either right here in this equation or right here in this equation, and you'll get one big equation you can solve now, which will give you the acceleration. Now, I know that you have a, y, and ax floating around in these things, but if you wanted to, we just discussed that a, y, and x are the same for these things, so this equation just be equated with just plain old a and just plain old a, to emphasize that these are two objects linked together by a rope, so they will have the same accelerations. So either way you decide to sort of process your symbols, you can get the acceleration to pop out once you have t. And then also you realize what you've done is that between these two equations here, you're really just solving two equations with two unknowns. A is an unknown and t is an unknown. Two unknowns and two equations you can always solve for. So that's where the primary answers for this problem are going to pop out. The last thing you can sort of do in this problem here is just do a bit of interpretation of this last one here, which doesn't seem like it's all that useful, but let's see what we can pull out from it. This describes the y acceleration of the block sitting on the table, this one right here. Well, what we know is that the block never levitates off of the table, and it never digs into the table, so what we can conclude from that is that the y acceleration of this block must be equal to 0. Because if it starts out with vy is equal to 0, just sitting on the table not moving, and we don't want it to move, if vy is equal to 0 and ay is equal to 0, it will never move, and that's sort of what the problem implies, because again, it doesn't say m2 ever levitates off the table or digs into it. So what we can say then is we can just set this ay is equal to 0 here, so we get m minus m2g over m2 is all equal to 0, so the normal force just becomes m2 times g, and you can put a box around that. Big conclusion, maybe, maybe not, maybe you knew that, but it's just a way of deriving what the normal force is equal to without any guesswork. So we get that the normal force, or the amount of flexation that the table is presenting on the block, is just equal to the weight of that block sitting on it, m2g. So it's just another result. It doesn't tie into the primary result of the equation, but it is something that's delivered by that Newton's law application right there.